Good morning to all of you. So maybe for 2-3 minutes just go through whatever we did in the last class, and in the meantime if you have questions you can ask, doubts. Yeah, maybe actually I have to wait for maybe about 5 minutes for MTech students design because they have class and that class gets over a little late.
So we told that stiffness matrix of two linear elements will not be same as stiffness matrix of quadratic. So if we see the problem example, to compare, it is not the same.
Yeah.
As told by yesterday. Similarly, the internal force vector is also not the same. Can we generate that internal force vector also will not be the same for all?
Yeah. So the question here is like know that rod problem we did using the two noded 2 element discretization and 1 element quadratic 3 noded element. So obviously when we saw the assembled stiffness matrix of 2 noded 2 truss elements and the stiffness matrix of just 1 3 noded element, they are different, and in general they will always be different. You know, if you kind of compare this kind of situations where it appears that no, in terms of nodes, 3 noded element, quadratic element has 3 nodes, which looks like no, if we just look at the topology in terms of nodes, so it is just the assembly of 2 noded 2 elements, but the governing element level governing equations are different. I mean, the assembled stiffness matrix of 2 linear elements, that is 2 noded elements, is different from the stiffness matrix of 1 quadratic element, that is 3 noded element. And also of course the generalized force, the internal forces when you see at the different nodes. So like we had in case of 2 noded it was assembly, so we had some internal force at the left, some at the intermediate and some at the end in general. Whereas in case of 3 noded quadratic element we had internal forces only at the boundaries, that is boundary nodes, starting node and end node. Intermediate node, because it's an internal, there is no cut section there, so there is no internal force shown there. So that was the question. So I mean, that's the situation always basically, you know, when you compare linear and quadratic elements. So that will be the all the time basically.
Global external.
Yeah.
Global external.
Yeah, that will also be in general different. Even the assembled load vector, external load vector will also be different in the two cases, because you know the corresponding stiffnesses are also different. So the load vector is also in general different. Yeah. Any other question?
Sir, is it possible to take different type of elements in a single structure?
Yeah, it is possible. You can have, say, part of the maybe the same rod problem, maybe part of it you can discretize using 2 noded elements, part of it you can also discretize using 3 nodes.
How will we assemble, because it's the stiffness matrix is 2 by 2.
Yeah.
And the next stiffness matrix is 3 by 3.
Right.
So
you can still, so yeah, maybe it's a good question. I will demonstrate you that. So I'll take an example, let the people join. So this question I'll take up. So suppose for the same rod, maybe one portion we want to model as 2 noded using 2 noded truss element and rod element, and some portion using 3 noded rod element. Then what should we do? That's the question. So then let me begin. So is there any other question? Yeah. Yeah, if it is at an angle, so you will have two components, and the component along the length of the member is basically axial force, but then you will have a transverse component of that force which will lead to bending also. So then we have to actually choose an element which has provision for both the axial deformation as well as bending deformation. So that will, when we will discuss frame element, that time we will talk about that. So if you have axial load actually as well as a transverse load. As of now, whatever we did, we can model only the problems where there is only force along the length of the member, axial force. Okay, so let me, is there any other question? So one other question was that if we actually, say we take a problem. So let me take again as an example that let us say that we have a problem, and let me also introduce a little more complexity in that. So let us say that we have this problem. This is a rod, again a stepped bar, and let me say that this is fixed here, maybe free or fixed here. Over this portion, let us say there is a distributed force, although I am taking this as an example, but what I am doing is applicable for all problems. And let us say that no, this length is same, so let me take a small l here also, although no, these lengths again can be different, small l here. Only thing is, let us say E is Young's modulus, which is same, but the cross sectional area is different. So Young's modulus is E, but cross sectional area is A1. Here Young's modulus again E, but cross sectional area is, let us say, E2. And you want to solve this problem, and this the distributed force, let us say that it is constant. And so one way, of course, we can always discretize the entire problem using two noded truss elements, but one possibility is that we discretize this using the first part, there is a distributed force, so that part let us discretize using a quadratic element, and the second part using linear element. Although you can have more number of such elements, but for the timing I am going to take one quadratic element for the left part and one linear element for the right part, and then let us see how we go about doing the assembly. So the discretization would be like this. So let me just sketch the line, center line of this. So first part we are discretizing using quadratic element. This, of course, the node is at the center of that. So this is somewhere here, and then this is the intermediate node, and then you have this node. So this is global node 1, global node 2, global 3, and this is global node number 4. This is one quadratic element, and second element is a linear element. Right? So you understand the problem that we have a distributed force over here, and no force over this portion. So it is actually there is no force acting on that. And discretization is, this is a quadratic element, obviously 3 nodes I am showing for the whole element, I mean this 1, 2, 3. So it's a quadratic element, and this is a linear element. And now we want to do the assembly. Element level governing equation, we already know that for the first element, the element level stiffness matrix would be, so if I look at the first element here, so for the first element level stiffness matrix is this EA by 3L. So that is EA upon 3, L is same, this only thing is area is A1, and then here we had what, 7, then minus 8, 1, and then this is minus 8, this is 16, and then this is also minus 8, right, and then this is 1, minus 8 and 7. Is this correct? And the corresponding external load vector due to distributed force, because there is a distributed force here, so that is going to be QL by 6, 4QL by 6 and QL by 6. This is the external load vector for the first element. Second element, if you look at, so in case of second element, the element level stiffness matrix is, so like when you use a, let's say, a package software and different types of elements in a structure, so depending on the element type, we'll call that particular subroutine and calculate the element level stiffness matrix load vector, depending on the problem, maybe other matrices or vectors, and then you will assemble them. So like let's say the first phase is to calculate the element level matrices. So this is for the first element, which is a 3 noded, and then for the second element it is simply EA2 by L, 1, minus 1, minus 1 and 1, and F external for this size actually a null vector because there is no distributed force here. So this is 0, 0. Internal force, of course, will be there. Now we want to assemble. So in the assembly, as you see now, since there are 4 nodes overall, global nodes, and each node has got 1 degree of freedom, that is displacement along the length. So the structure, if you look at the assembled system matrix, that is going to be, so let me write it here. I think this you know already, I have just written what we have done earlier. So let me write here so that I have more space to write the stiffness matrix. So your left hand side, this is your stiffness matrix. The vector of unknowns is global unknowns u2, u3, u4 is equal to, right side you will have this external load vector contribution, and this side internal load vector contribution. So first let us look at the assembly of the first element. First element corresponds to global nodes 1 to 3. So its contribution will go to first 3 nodes and columns. So E by L is actually same in both cases. So let me take that as common. So here you will have E by L here, and then what you have is 7A1 minus 8A1 and A1. That is 7 minus 8 and 1. So the first row of stiffness matrix of the first element, the 7 minus 8 and 1, goes to basically first row and 1, 2 and first 3 columns, because it is consisting of first 3 global nodes. So first this element goes to first row and first column, this goes to first row second column, this element goes to first row and third column. So same way the second row will go minus 8, yeah, sorry, this 3. So yeah, 3 let me put inside, we multiply 3 there. So let me keep it outside, we'll multiply there. So this is 8A1, this is 16A1 and minus 8A1. Then the third row is again A1 minus 8A1 and 7A1. So this is the contribution to stiffness matrix from the first element, which is a quadratic element. Now let's go to the second element. So the second element is now the stiffness matrix is this, and it consists of its starting node is global node number 3, in node is global node number 4. So its first row will go to third row and corresponding columns, and similarly fourth row will go to second row will go to the fourth row of the global matrix. So that means actually this element will go to third row, third column, because the starting node of first second element is global node number 3. So the contributions would go to third row here and third column. So that is here, which is basically A2, and since we have taken 3 out, so let me just write that as plus here 3A2, and then here we'll have minus 3A2, and then the second row will go to basically fourth row, columns 3 and 4. So we'll have minus 3A2 and 3A2 here. If you would have taken this 3 inside, so it would have been in the division here, and then this is simply plus A2 minus A2 minus A2 and A2. And wherever we don't have any contribution, so those terms are actually 0. So this is 0, this is 0 here, 0. No, only 1 0. Yes, it's only 4 columns. I'm sorry. So so this is only 4 columns. So you have only that. So this I just wanted to put little below. So that's why I wrote it. So this is the assembly of one quadratic element and one basically linear element. In the first portion you can have 2 quadratic elements, in the second portion you can have more linear elements and so on. So this is how you actually do. So once you understand the connectivity, that each element, what are the its first node, second node, third node, depending on the kind of element you are using, then you understand that in the global matrix which row and which column will actually correspond to local rows and columns of the stiffness matrix or load vector. So here the numbering was such that the first 3 rows and columns are the first element, and then the third and fourth rows and columns here are for the second element. You can actually change the numbering, and then you can again do that. So now if you look at the right hand side, so we have the load vector from the first element will go to first 3 rows, so which is basically QL by 6 and 4 QL by 6, QL by 6, and second element has no contribution, so that is plus 0 here and 0, because Q is 0 there, second element. If it was non-zero, then you'll have to put that. QL by 2 and QL by 2 you'll have to put additionally. Now if you look at the internal load vectors, so we have at first node here from the first element, so minus Q11, second is the intermediate node, so there is no internal load there, and then here we have from the first element, from the third node of the first element, this is the contribution of internal forces to the global internal load vector. Then we bring in the second element. So for the second element is again here, say Q1 2, and then here we will have Q2 2. That is first node internal load at first node of the second element, and this is the internal force at second node of the second element. That is superscript 2 is for the element. So this is how the assembled system would be. So is this clear? Like, the question was how to assemble two different kinds of elements. In this case, one quadratic and one linear. And we can have more such elements, and you can do the assembly in a similar manner once we understand the logic. And then of course the remaining solution is that then you write the boundary conditions. So boundary is a very good question because it demonstrates how we use different kinds of elements. So the boundary conditions are, as you know, the left and right ends are actually fixed. So u1 and u4 are 0. So one is that u1 equal to 0, another is u4 equal to 0, and at the node number 3, global node number 3 here, as you see, if you draw its free body diagram taking a cut section here and here, since there is no external concentrated force there, so actually this difference would be equal to 0. So that is, these are two boundary conditions, and then you have Q31 minus Q12 is equal to 0. So then you see the number of unknowns will be U2 and U3, these are already 0, and Q11 and Q22, these are 4 unknowns. So first again you can take second and third equations, solve for U2 and U3. Once you have got that, then you can calculate the these reaction forces at left end and the right end from the first and fourth equations. And once you have done that, then within the element you can calculate displacement at any point, and also you can calculate your say stresses. You will find in this case again it is going to give you exact solution, because here due to a distributed load the variation of u is going to be quadratic, and here there is no force, it will actually be linear. So this will give you exact solution. Of course exact within the assumptions made in 1D, because here there is a discontinuity. So actually one dimensional analysis is not applicable there, because there is going to be some stress concentration here. So a little away from that, whatever we get would be close to reality, as long as the cross-sectional dimensions are much smaller compared to the lengths. But of course here we will have discontinuity because of that stress concentration, which we cannot get of course from this model, because we are idealizing the problem as one-dimensional problem. So yeah, so this is one question which was asked, a very good question to actually demonstrate this. So then today, is there any other question in between? Is this clear? So okay, so then one more problem I want you to take. So far we just dealt with a problem in say Cartesian coordinates, so it's only one x coordinate we were using. Sometimes you will have to deal with problems in say cylindrical coordinate system. Again we are talking about 1D problems, so we'll look at the idealization in that. So let me consider a problem. Let's say we want to formulate a problem that is heat transfer in a long cylindrical pipe along radial direction. So heat is actually flowing along the radial direction. I hope I know you are also interested in problems other than solid mechanics problems, so like heat transfer sometimes. So we are only of course going to consider only conduction. So what it actually means is that you have a hollow pipe, and it's very long. So we are assuming that there is no temperature gradient along the longitudinal direction. There is only temperature gradient along the longitudinal direction, along the radial direction. So there would be heat flow only along the radial direction. So then it is enough just to model cross section of the pipe, and we can solve the problem. So the situation is like this, that we have this is, let us say, the inner boundary, and this is the outer boundary. It might have certain radius, say inner radius is capital Ri and outer radius is Ro, and maybe you have different boundary condition. Maybe a temperature is specified here, maybe convection is specified here, or both the ends temperature is specified. So the different boundary condition. But first we are interested in formulating the problem, that is developing the element level governing equations. So obviously for this, and I mean if you take any other point, so it has a radial coordinate r. No, so some point here is at a distance small r. So small r is the radial coordinate measured from the center of the cylinder, and the temperature gradient is only along r. That means temperature is only function of r. So heat transfer, as I said, is only taking place along the radial direction. So first we need to one more thing is the problem is, let us also say that it's an axisymmetric problem. So no, the situation is whether I consider at some angle here or some angle here, everywhere the situation is identical, that is temperature distribution is independent of theta coordinate. So we are also saying here that it's actually axisymmetric problem. And then temperature is going to be only function of r. So first we need to develop the differential equation. So for to develop the differential equation, what we can do is take a small element somewhere out here, and I think maybe you would have derived some other point of time this kind of governing differential equation. So let us say we consider this element and draw the energy balance diagram for that. So let this, that's the inner surface, then you have this is the outer surface. I am just isolating that, and somewhere here is the center. So this radius is r, and let us say this is delta r, and then the angle subtended here is, let us say, delta theta. So let us say that the heat flux, that is heat per unit area, and we are going to consider a steady state problem, so not the time dependent problem. So let us say heat flux entering here, that is heat per unit area is QR, and heat flux leaving out is, let us say, there is going to be change, so QR plus delta QR. So this is and also let us say that inside this there is some heat generation, so let us say that is heat generated per unit volume. So this is the now we apply the energy balance in this, which is actually heat energy. So if you apply energy balance, let me take the incoming and generated energy as positive. So this is per unit area. So you will have QR into area. What would be the area of this phase? That would be R into delta theta into actually perpendicular to the plane here, but we are that means length has to come, but along the length nothing is changing, so we can take unity, or any length you can take. It is basically going to be the same situation. So let me take a unit length along z direction. Length of the cylinder is just unity. So actually a long cylinder, but we are considering this segment of unit length, because along the we said only temperature is a function of radial coordinates. So along the z also it is not changing, so I can take any length. Finally it is going to be there in all the terms, same thing, so it will cancel out. So let us say this is the energy entering at this left phase, and then energy leaving out from the right phase would be QR plus delta QR into area. What would be the area there? So at that place you will have to multiply. So this area is going to be R plus delta R into delta theta. This area, so this circumference is going to be, a perimeter is going to be R plus delta R into delta theta, again into unity. This is heat entering here, this is the heat going out, then there is a heat generation, so we will have plus QZ and into volume. So volume I can now write as R into delta theta into delta R. So R into delta theta is like, of course you can always write that as R plus delta R by 2, but that finally will actually cancel out in the equation. So I am taking average volume as R delta theta is the this circumference into delta R. I am approximating the volume into 1, that is along the z direction, is equal to 0. So this is your energy balance, right? So now if you simplify, what do you get? So this term of course is as it is, so this and its multiplication with this is going to get cancelled. So that is this QR into R into delta theta will cancel out with this. So what you will be left with is minus, then you will have this QR multiplication with this delta R into delta theta. So that would be one term, right. So this QR into R cancelled out, QR into delta R into delta theta is one term, and then we have minus this delta QR into R into delta theta would be one term, then we will have minus delta. Please just simplify this and tell me what you are getting. So delta QR into delta R into delta theta is another, and so yeah, so these are the three terms, right. So one we have already cancelled out, plus you have of course this QZ into R into delta theta into delta R is equal to 0. And now if you look at what I can do is these two terms, if you look at here QR delta R, this is delta QR and R, so the first two terms I can write as basically minus of delta QR, this small r is actually subscript, so that you should keep in mind, into R into delta theta. So that is these two terms, no, QR delta R, and this is delta QR into R, so it's like delta of QR into R, and of course into delta theta, and then minus you have of course this delta QR into delta R into delta theta plus QZ into R into delta theta into delta R is equal to 0. So this is just the energy balance equation, and now we want to derive the differential equation. So you need to first divide it by the volume of the element considered differential element, and then take the limits when delta R and delta theta are going to 0. So as you see, the first term after dividing by the volume we will be left with delta of say QR into R divided by R into delta R. So this is what we will be left with, when you divide with R delta theta will cancel, R delta R you will get here, minus here you will get delta QR and divided by R plus QZ is equal to 0. Now you take the limit, delta R tending to 0, delta theta tending to 0. Anyway, delta theta is again going to be actually independent, so there is finally delta theta also has vanished, so this is good enough to say that delta R is tending to 0. So this will transform to a differential equation which will be minus 1 upon R d by dr of q subscript R into R, that is the first term, and this will be in the limit when delta R is going to 0, delta QR will go to 0. So this term would actually will go to 0, you will have QZ finally equal to 0. So this is what you will get as the differential equation, but now it's in terms of QR. You can of course always do what you can do, multiply by a minus sign, so you can also write this as d by dr of, so there is no difference, I mean you can write in that way, minus QZ equal to 0. See, the same can be written like this also. Now we bring in the constitutive relation here, that is Fourier heat conduction law, which would be which will give you QR is equal to minus K into dt by dr. Now QR is, as you have seen in the free body diagram, is a heat flux, heat per unit area. So it's only minus K into dt by dr. It's not the total heat, but it's a heat per unit area. So if you substitute this constitutive relation, then final equation would be, as you see, minus, if I write outside, so 1 by R d by dr of you have R into K dt by dr minus QZ is equal to 0. So is this okay? So this is finally the differential equation you get. Now what we are interested in is doing the finite element formulation for this. If we want to solve this problem using finite element, so first thing is to develop element level governing equation. Now straight away we do not know, like no kind of strain energy, potential energy of the forces, so we will have to go through the weighted residual weak form, and then we can see if we can get to the integral functional. So first would be weighted residual statement. So this is only the just the derivation of the differential equation. I thought that let me do, although I could have written directly this differential equation. So now you have this as your differential equation. You write the integration. Now when you write the actually the integral here, so how should I write the? Of course you'll have to take the weight function. Let us say W, and then you have thinking that we are going to substitute approximate solution in place of T. So we will get this as the residual itself, which is minus 1 upon R d by dr of R into K into dt by dr minus qz. So let me put this as a square bracket. So then this is only one. Here now what do I do for the integration? So one question, maybe one answer could be simply I put dr, like we were putting dx, so I can put dr. So is that right? See, actually the this weighted residual statement is written based on the integration over the entire volume. So here again you have to take actually the volume, and so the volume would be, because here nothing is, no w is also going to be function of r, this entire thing here what we write is only function of r. So I can write the volume as 2 pi r dr, and then along the length the actually the dimension is unity, this is equal to 0. So this would be actually your weighted residual statement. So that actually 2 pi is a constant, you can just divide the whole thing by 2 pi. So really this can go out, but it won't be simply r dr, but it has to be r dr. So what is important is when you are writing the weighted residual statement, the integration of the residual with multiplication with the weight function is over the entire volume. Because in case of 1D problems when we were trying to write, we were assuming that cross-sectional area, of course the volume would have been there a into dx, but the cross-sectional area within the domain we are considering is if it is constant, these things do not change. So but here because r is r dr, and r is going to change because this r which is coming in your volume and changing along the radial direction, so this is going to change this equation. So it is important to keep this term here in this case. Of course, as I said, you can always divide it by 2 pi and take that out. So this will be your weighted function, and then since finally we are left with dr, so the integration would be from the lower limit to upper limit. And let us say now these limits I want to put for an element, not for the entire domain. So if I look at the radial line, so this is, let us say, my radial line. Somewhere here is my axis of the cylinder, and as I said, this is your Ri, and then this is your Ro. So what I'll do is when we discretize this into a number of elements, so let us write this equation, weighted residual statement over only one element. Let us say this element, we write this. So then this integration, now one more thing I am going to do, if you look at this differential equation, is actually differential equation with variable coefficient, that you see here r is coming. So of course again I have an option to take the origin of local coordinate at the first node of the element, but then this r is a global r, that is radius of the cylinder at that point, so that has to be taken care. Other option is that we write our approximate solution in terms of the radial coordinate. So my origin for radius is basically here, radius is measured from the axis of the cylinder here. So let us say that in that case the radius here is Ri, and the radius of this point is, let us say, Rj. Starting node radius is Ri and end node radius is Rj. This change I am making compared to what I did earlier is just to account for because there is a r here coming in, so differential equation with variable coefficient. Although we can do in that manner, I can take say some r bar with origin here, but then I have to write r in terms of, because wherever this small r is coming, finally during the actual integration I have to write this small r, which is actually radius at that point, r bar plus the radius of the first node of the element. So it can be done in that way, but here I am just saying that let's say this integration is from Ri to Rj. So this weighted residual statement is now over an element. We are not writing over the entire domain of the problem under consideration. So now first step, as we see, we can do the integration by parts. Interesting thing is, see, you have 1 by r in the differential equation and this r here. So in the first term they will actually get cancelled out. So the first term you will see that is going to be integral Ri to Rj w, and this r gets cancelled. So you have, first let me write that, d by dr of rk into dt by dr, and 2 pi I am dividing. So let us, the whole thing is divided by 2 pi, so you get just dr in the first term. Because this in the first term there is 1 by r here, into this r they will cancel out. So that's the first term. Then the second term of course is minus, again integral Ri to Rj w into qz into of course RDR. 2 pi whole thing you can actually divide because it's immaterial, multiplying the whole thing by 2 pi doesn't matter. So then now because no the derivative here, temperature derivative second, whereas W no derivative, so we can do the integration by parts once. So what I will get is W into Rk into dt by dr, the whole thing evaluated at Ri and Rj, and then minus there will be minus sign here, and then plus integration from Ri to Rj dw by dr into Rk into dt by dr. So this is what you will left with the second term. No, that integration, I am just doing integration by part what we did earlier. And the only thing is no, the problem simplified because we have one r here and 1 by r here. Suppose no, if this r was not there, no, or we make a mistake. So one is that it is wrong to just take no integration over dr, and another difficulty it would create because then you will have 1 by r left out here, and then the integration by parts would not be easy to do. So see the nature how it is. No, your differential equation is such that no, it ultimately simplifies this. So now I remember one of my friend at IIT Kanpur. So one day he called me. He's working on a circular plate and doing some approximate analytical solution. So in that process, some of the terms 1 by r, and he's having some r somewhere in the approximation function, so they get cancelled out. But he has some term which does not get cancelled out. So when he's trying to do the integration, it goes to infinity. So see that is the kind of problem you sometimes have to handle. Of course, then the option there was to appropriately modify the approximation functions. But I mean, you see the beauty of the problem that this r and this r gets cancelled. So you have a simple integration to do here. So I mean that's how the things come here. So then second term is of course Ri Rj W Qz Rdr is equal to 0. See, now if you want to do the finite element formulation, one option is that we can actually do from here, we can get to the integral functional. So only thing I would do that the value of this k into dt by dr, I am going to maybe I can include in both these terms together, even including r, in the secondary variables. As if you look at the primary variable of the problem is going to be t, because there is only one boundary term, and in that only w is there. So primary variable is going to be t, and secondary variable is basically dt by dr. But since the boundary term involves the product of these two functions, we can give some name to this term. So now what I can actually do is this particular term I can write as, say, the upper boundary, it is going to be minus w evaluated at upper boundary, and let us give some name to that. So minus w at upper boundary, so at Rj, and this is, let us call at some capital Q at the upper boundary, that is Qj. So this w of course is evaluated at r equal to Rj. So this is, let me put here as evaluated at Rj. Then the lower limit will be plus, and you will have w evaluated at Ri, and let us say the corresponding value of this quantity at r equal to Ri is Qi. So and rest of the other two terms basically remain same, that is this term plus the next term is equal to 0. So only thing what I have done is, see, your Qj is nothing but Rk into dt by dr at r is equal to Rj, and Qi is essentially Rk into dt by dr at r is equal to Ri. So that's the notation I am using here for this secondary variable, denoting it by Q, and its value at ith node, that is at Ri is Qi, and at Rj it is Qj. So this is the notation I am using. Now as I said, let W be delta T, that is variation in T, the way we did earlier. So then you can see that this term can be written as essentially your big form minus this now delta Rj, the delta T at Rj. So let me call that as value of T, delta T at r equal to Rj as delta Tj, and value of delta T at r equal to Ri is, let us say, delta Ti. So I can write then, once I take W is equal to delta T, the first term can be written as minus of delta Tj Qj plus delta Ti Qi. Is this okay? It's just the notation. W I am taking as delta T. So now W at Rj would be delta T at R equal to Rj. That I am denoting as delta Tj. That is variation in temperature at J and variation in temperature at I. So this is the now first term, this is the second term, then you have the integral terms. So the integral term is plus integration from Ri to Rj and the derivative, so that is d by dr of delta T. That is the first term we have, because in place of W I am writing delta T. The second term is Kr, of course, into dt by dr dr. That's the this particular term. And the last term, of course, remains minus integral Ri to Rj, and then you have delta T into R into dr into Qz. We have this term. W is written as delta T Qz R dr. This is equal to 0. So now we are ready with this function here. We can derive the integral functional out of this the way we did earlier. So now you can say that this is actually delta I equal to 0, where your I is the integral functional is. See, I am going to take out delta here. So these we are not taking unknowns from the variation point of view. So delta can be just directly taken out. So here I would write that as minus Tj Qj plus Ti Qi. In this, because you first the derivative with respect to R and variation are interchangeable, so this can be written as delta of dt by dr, and then it is now coming, this is a known quantity, so there is a variation only in T. So the second term can be written as half of integration from Ri to Rj, and then that is basically Kr into dt by dr whole square dr. And of course the last term is minus integration from Ri to Rj T Qz R dr. So this is your integral functional. This is exactly the way we did for the earlier problems, taking out the variational operator delta common. So here it comes as it is, here it is comes as it is. From the variation point of view, this is treated as constant, this is treated as constant. So you just take out delta out here. This is first you are interchanging the variation and derivative. So that is you are writing this as delta of dt by dr, and then you are taking out common from delta operator common from whole other term. So you write it as like x square by 2. So it's like x dx is d of x square by 2. So this is what you get finally. Similar thing we did earlier, 1 by 2 Ea du by dx whole square. So it's essentially the same concept. Now you have got your integral functional. Next comes the finite element formulation. Now as you see, the highest derivative involved either in the weak form or this integral functional is first derivative. So minimum polynomial will have to work with is the linear in R. So now approximation within the element. So I can take T as like A0, that's minimum thing. Of course we can always take more number of terms as we have seen. T equal to A0 plus A1R. This is the approximation of T temperature within an element. Now we need first to express A0 and A1 in terms of the values of T at those two nodes. So the element we are considering here is that the R coordinate here is Ri and R coordinate here is Rj, and origin is the axis of the cylinder. So this is where you are measuring your R from. And so first we are saying that T equal to Ti at R equal to Ri. So this equation becomes A1 Ri and Tj is value of T at R equal to Rj, so you get A1 into Rj. If you solve these two equations, you can get your A0 something and A1 is equal to something. You can do that. So what you can do is, if you subtract this equation or let's say the second equation from first, you can straight away write A1 would be simply Ti minus Tj divided by Ri minus Rj, isn't it? From these two equations you can write A1. So then once you get A1, then you can write your A naught would be Ti minus A1, which is Ti minus Tj divided by Ri minus Rj into Ri. So this is your A naught. So you get your A naught and A1 by from these two equations. Then you substitute it here. So finally you get your T. Now you are going to put A0 expression here and A1 expression here. Then you collect the coefficient of Ti, that is one shape function, coefficient of Tj is another shape function. So let me write those shape functions as, I am going to write as those shape functions as n1, n2. So let me say finally that I can write this as n1, n2 and the vector of elemental degrees of freedom as Ti and Tj. Okay. What would be n1? Yes. What would be the value of n1? So essentially the difference Rj minus Ri would be actually equal to length of the element. So let us say the length of the element is L. So you can actually you have to put these values here, collect the coefficient of Ti, that will actually give you n1, and that you would see would be you can see that it has to be R minus say Rj minus R divided by L, which is Rj minus Ri. So L is here, as you see now, L is Rj minus Ri. So this is what would be your n1. You can rewrite that, and second shape function would be R minus Ri divided by L. Again the property that n1 should be unity at first node and 0 at second node. So if I for the first node R is equal to Ri, so Rj minus Ri, which is L, so L by L is unity, and at R equal to Rj, n1 is 0. So n1 is unity at first node, 0 at second node. Similarly, if you look at second shape function, if I put R equal to Ri, it's 0. So n2 is 0 at first node, and if I put R equal to Rj, it is unity. So we this is the same property which we said. So over the element, when we go from this ith node to the first node of the element where R is actually Ri and the second node R equal to Rj. So the first shape function n1 is going like this. So this is unity here, and if you look at the second shape function, this is how it is varying. So this is your n1 variation and this is your n2 within the element. So this is your interpolation. Again rest of the things go in a similar manner. So B said this we can call it as interpolation matrix H, and that vector we can call as D. So your D is nothing but this, and this is your H. Then you need also dt by dr. So then dt by dr is actually going to be derivative of H, so which is dH by dr into dE, and this we call as actually B, similar to what we did earlier. So we can call this as B into dE, and where now your B is nothing but actually dN1 by dr and dN2 by dr. And if you substitute the further shape functions right now we got, so this is again going to be minus 1 by L and plus 1 by L B for these shape functions. Now these shape functions we have written. They are exactly same what we did for the rod element, truss element, whatever derivations we did. Then now can you now work out the expression for the element level stiffness matrix, load vector, everything out of this? So you have to just rewrite this, as I said, you put the transpose and so on. So the integral functional then can be written as, so you have to substitute these approximations. So I can write, let me first write the integral term, which is half integration from Ri to Rj. Then I can write this, of course, R into K anywhere, and then dt by, because it's a scalar, dt by dr whole transpose into dt by dr, and then dr, that's the first integral term. Then the second term is minus Ri to Rj. Then we have, I can say T transpose into R into Qz into dr, that's the second term. The last one you can write actually, the transpose of this Ti, Tj transpose, and then you can put the first term is actually plus, so minus Qi and plus Qj. This the first two terms. These two terms I have written at the end. This I have written first, the second, this is the last term I have written there. So it is straightforward from there. And now you put here dt by dr as B into dE and take the variation of I equal to 0. So finally you will get the element label. The steps are same, no, the similar steps be followed for the first derivation. So element level then governing equations would be okay. So that is going to be again the form of the governing equation is same, that is you can say you will get a Ke into dE is equal to F external for the element and plus F internal. This Ke is coming from the first term, only difference is where this Ke would be equal to integration from Ri to Rj, and then you have R into K into B transpose into B into dr. So that is your Ke. It's coming from this term we had done earlier, no? So I am not repeating that, but if anyone has a doubt, no, you can ask after the before or after the class. And then F external is coming from basically this term, so which would be integration from Ri to Rj, and then you have essentially this, no, H transpose R Qz dr. And your F internal for the element is basically, this vector you are taking it to the right hand side, so both these become plus on the right hand side, so it's simply minus Qi and Qj. So this is the element level governing equation you get for this problem. So the structure is same, only thing what has changed is finally you have this here R sitting. So similarly in this load vector also you have this R. So you need to do that integration, and then of course the discretizing the whole problem into a number of elements and then imposing boundary conditions, and solution remains exactly the same. Only thing is because now this R is sitting, so for different elements you will have, even if say K is constant throughout, Qg is constant throughout, but since this R is coming in the integration, so your element level stiffness matrix will be different for different element because of this term R. When you are doing the integration. So rest is now actually integration and of course the solution of the problem. Of course in this case you can actually write the integration. So what would be Ke? Let us say we want to work out Ke. So what would be Ke? Assuming that let us say this thermal conductivity K is constant within the element, so that I can take outside, and then you have integral Ri to Rj. This is R is there, and B transpose B, as we have seen earlier, would come out as 1 by L square minus 1 by L square minus 1 by L square and 1 upon L square, that B transpose into B into dr. So this is what you will get. So you finally see that this is K, because all these terms are constant, so you will get only this term R square. It's and when you put the limits, so you are going to get basically Rj square minus Ri square by 2. And into, of course, so if I take L square out here, so you'll get 1 minus 1 minus 1 and 1. So this would be the integrated stiffness matrix. And this Ri Rj can be written as Rj square minus Ri square can be written as Rj plus Ri into Rj minus Ri. So finally what you can say that K into this term Rj plus Ri divided by 2L, because Rj minus Ri is equal to L, so you can actually write this like this, minus 1 and 1, the way I just said. And you can say that this Rj plus Ri divided by 2 is nothing but average radius of the element. So I can write now that this is K into R average divided by 2L, but this is for that particular element, and for different elements this average radius is going to be different. And into, of course, 1 minus 1 minus 1 and 1. So this is your element level stiffness matrix if thermal conductivity K is constant. So it just can be finally, 2 will go out, sorry, when I say average this 2 will go out, so this is what you will have. So this Rj plus Ri by 2 is actually your Ra. So Ra is Rj plus Ri by 2. So similarly, if you want to evaluate the external load vector, so the external load vector would be again the integration from Ri to Rj, and then you have Qg into R, and then the shape functions. So the shape functions are, one was Rj minus R divided by L, and second shape function was basically R minus Ri by L. So in this, of course, you'll have to do the integration properly into dr, that r I have written here. So this integration you have to do, because this first term is of course one set of terms you have constant. Of course qz you can take out, assuming that is independent of r. So qz by L can be taken out, then you'll have to integrate. The first term is r into rj minus r square and minus ri into rj. Do the integration and you can simplify that. And once you have done this, then the solution of different types of problems are here. Say for example, you want to look at a problem. Let us say that we have a cylinder, and here there is some temperature T naught. Outside temperature is T naught. The inside temperature is T naught. The inner surface, inner radius is Ri, and the outer radius is, let us say, Ro. And the outside there is, let's say, convection, or maybe dt by dr is 0. Let's say that kind of a situation you have. So or there is a convection here, or there is a temperature specified, or maybe let us say that the outer boundary, the temperature T actually equal to 0. Now we want to look at the temperature distribution, that the inner surface is maintained at a certain temperature, the outer surface is maintained at 0 temperature, and then what is the temperature distribution along a radial direction. So you have to discretize this into a number of elements. Maybe the starting point is, see, if you one element discretization means will give you the same value T naught here and T equal to 0 outside. So at least if you want to get some intermediate information, it should discretize at least into 2 elements. And so let us say this is element 1, this is element 2, this is global node number 1, global node number 2, this is global node number 3. And then you have to assemble the equations in a similar manner. As you have seen, if for first element this is, let's say, at the center, so accordingly you can calculate what is the average radius, you get the stiffness matrix, this basically coefficient matrix, and then similarly for the second element the average radius would be different, and therefore its stiffness matrix, this is going to be different, but the overall steps are going to be same. So that is when you get the global system level equations, you will have T1, T2, T3 if you are discretizing into 2 elements, and this side you will have contribution from the heat source which is present there, and if that is 0, then this would be 0, and these are your internal boundary terms. And then at this place, if there is no point heat source, then the difference of the Q term coming from the left and right would actually be 0. So after assembly, imposing the boundary condition, that is T1 is known, T3 is known, from the second equation you can solve for T2. Once you solve for T2, then you can find out how much flux is actually coming at the inside surface, how much flux is going out on the outer surface. So this is how you will solve this kind of problem. So why I took this problem, because only difference is that it's in cylindrical coordinate system. So rather than doing the integration like dx we did earlier, r dr you will have to do, and it's a differential equation with variable coefficient. So even if your properties like thermal conductivity is constant through the radius, but still you get the stiffness matrix which depends on where the element is lying, that is on its average radius. So I think I'll stop here, and if you have any doubts and questions you can ask. And maybe then next week Monday class I will start basically Euler-Bernoulli beam element. So I'll start with what are the basic assumptions in Euler-Bernoulli beam element: displacement, strain, stresses, then strain energy, and corresponding differential equations, and then how to formulate the element level governing equations for that. So the message from here is that similar kind of problems you should be able to develop element level governing equations and should be able to solve such problems. Okay, yeah, that's it.